Well, Otto gave us a very nice overview of a really aggressive, real-time, comprehensive water management program that's going on in Los Angeles. And there are parts of the country where this is absolutely essential. And as Adele mentioned, there are other parts of the country that have a lot of water, such as the Great Lakes area. So they don't necessarily have to be as concerned about the availability of water. However, in the long run, water availability becomes an issue for almost everybody. And so the concept of recycling is essential. First of all, I think we all understand that all water is recycled. Nature recycles it for us, and we also recycle some of it ourselves. But the other thing that we need to also appreciate is that the technology is here today to recycle any water. We can take any wastewater, let's say with the exception maybe of having too much tritium, and we can recycle it for any purpose. And the key issue then is, what are those purposes and what kind of water quality characters do we need for each of them? And there are many possible applications and uses: irrigation, cooling water for industrial operations, of course drinking water, and many others. But the key to all of them really is source control, because the objective here is to select the appropriate technology to convert the wastewater into a usable and safe product. But it's necessary to have a good understanding of what's in the source to then determine what the appropriate treatment technology is going to be needed to assure that the end product meets the quality spec for the end use. So that's really the key, the engineering process of determining what's the right treatment train, what arrangement, and how do you run it. Now, as we think about water and human exposure, like drinking water and some other applications, there are two general categories of risk that we think about: acute and chronic risk. And one of the things that I think we need to understand as a society and as regulators is that well-managed, well-designed, recycled water as drinking water is actually better quality water than the typical conventional drinking water supplies that we have. And so I think it's important that we have a rational approach to determine just what the specifications need to be to assure the safety and the quality and public acceptance. And those requirements are typically described for microbial contaminants, which are the acute ones, in log removals, and for chemicals, margins of safety. But in addition to safety and water quality, of course, aesthetics is important. If something's going to be a drinking water, it needs to be acceptable to the public. And of course, always sufficient quantity, a very high level of reliability, 100.0% reliability, because we don't want interruptions in water supply and distribution. The key to it all ultimately is monitoring to be sure that the water that is being produced along the way and being distributed is meeting all the specifications. And some of those are health-based specifications, but many of them are not health-based. So one monitors for a variety of endpoints to assure acceptability. And then the bottom line, as Adil was alluding to, was public involvement, because the public perception is key to all of this. If the public will not accept it, if they will not accept recycled water, then they won't finance the construction of the systems. And it's really, when you think about it, it's really a very separate issue whether the public will actually drink the water that is recycled. because history shows that there's really a kind of a right brain, left brain mentality about this. People intellectually believe that the water is high quality, but sometimes emotionally they aren't quite able to accept it. So there's a whole public education, public perception adjustment that's needed. Well, let's talk about some specific categories of recycled water. Certainly, as I've alluded to, mostly potable, and that's described as direct and indirect potable reuse. And that can be included in municipal drinking water, even small individual facilities. There are even systems that one can purchase to recycle the water in an individual home as well as in a building, both for drinking and for also non-potable applications. As Adel spoke about groundwater recharge, it's a really key process for storing that water. And ultimately, it can even be a treatment process. And of course, there are many applications in food processing. And in food processing, drinking water is needed. The water has to be potable in the United States to be allowable to be used in food processing. Now, on the non-potable side, there are many other applications which are actually much higher volume uses, such as sanitation, flushing, many other domestic uses, just washing cars, watering lawns, etc. Golf course irrigation, for example. And so I think it's important to realize that the current paradigm that we have, where we provide water for all uses, including drinking water at the tap, is not really the most efficient way to do it necessarily, because these other uses are frequently higher volume need. The amount of drinking water that's consumed and used in cooking per day per person is about 1% of the total amount of water that's in that distribution system. So we need to think about alternate ways of being more efficient and providing higher quality water for its particular need and other qualities of water for other needs, other uses. And for example, in the commercial and industrial areas, cooling water, of course, doesn't have to be potable, but it needs to be non-corrosive and appropriate for that use. On the other hand, there are commercial uses that are, for some processes, water that are ultra-high purity and much greater quality specification than needed for drinking water, for safe drinking water. But then there are other applications that don't really require very high quality water, such as cleaning apparatus and so forth, for example. Doesn't have to be drinking water. And even maintenance, for example, washing the trucks for that factory doesn't need to be drinking water quality, but it needs to be safe because there can be worker exposure. So what about quality specifications that one deals with in human and non-human, non-potable applications? Well, for human exposure, there's consumption, ingestion, but there's also contact. There is inhalation, for example, from showering, and aerosols. And we know that the most significant public drinking water issue in the United States, the most significant risk in drinking water in the United States is legionellosis from inhalation of aerosols, because the organisms regrow in the plumbing. And then there are other contact applications that occur, of course, bathing, showering, and just miscellaneous contact. On the potable side, the microbial content is the most important because it's the acute risk, and it can be rapid, and it can be significant, and it can be fatal. The good news is, in the United States and in most developed countries, the water is virtually universally safe from a microbial content. On the other hand, as we become more sophisticated, we become more and more sensitive to issues relating to trace chemical content and potential lifetime risk that can occur from consuming the water for 70 years, which is the default numerical value that's used when one does these calculations. But keep in mind, the reason we're concerned about trace chemical content is because water analytical chemistry has progressed very rapidly to the point where it can now identify substances in water that 10, 20, 30 years ago could not be detected. And the more of these that we can detect now at the lower and lower concentrations, such as parts per trillion and parts per quadrillion, raises issues. But at the same time, keep in mind that the lower the concentration, the less the risk. So we're identifying more things, but the actual potential risks are probably much less. In addition, on potable water, it has to be corrosion control must be a very important managed issue. The issue of Flint, Michigan last year was simply corrosion control. The water that they were putting into the system was too corrosive. It extracted metals from the pipe, including lead, and that resulted in all of the problems that have been in the papers where I live about once a week, even this many months later. So corrosion is key. Corrosion control is key. On the non-potable side, microbial contamination is still paramount. And that's because there can be human exposure, such as from industrial uses and from aerosols and even washing uses. So again, that's the key. The chemical side is much less than it is with potable because there's much less human exposure potential, since these other non-potable uses do not involve ingestion. But other water quality characteristics are still important too. So let's talk about some potable water specifications, and particularly in the relationship to recycled water. Now, we know that drinking water standards have been in existence in the United States initially almost 100 years ago from the Public Health Service standards, which were not universal, but in 1914, actually, the first set of Public Health Service drinking water standards were produced. So there are about 100 substances that are currently regulated in drinking water standards. There are several hundred other substances that we have values as guidelines. And in fact, many countries, including many states in the United States, are producing guidelines for indirect potable reuse and direct potable reuse for drinking. The World Health Organization has drinking water guidelines, and it is in the process of producing guidelines for recycled potable water. Australia has guidelines. California has some guidelines and is working on standards. Texas has some guidelines and is formalizing those. Even some European countries are working on guidelines. And in the United States, in addition to our regulations, we also have these health advisories, which are not regulations, but many states kind of automatically convert them into regulations, which in one respect is good, but in another respect is not appropriate. For example, in the case of PFOS, the perfluorophosphonate compounds, EPA issued a health advisory for them a couple of months ago based solely on conservative health protective issues, but many states converted them directly into drinking water standards, which actually is kind of excessive regulation when you get down to it. So regulations are complicated, guidelines are complicated, but there are plenty of them around there, but more to be had. But keep in mind that when we're talking about potable reuse, we're producing drinking water. And as I said, we have 100 years history of drinking water specifications, and they've been amplified over the years. The Safe Drinking Water Act was ultimately issued in 1974, and EPA produces those standards and treatment requirements. And it's relatively safe to say that nowadays the drinking water in the United States is safer than it has ever been, believe it or not. It's highly treated mostly. Source waters are more protected than they ever were. Much more monitoring and surveillance is conducted to assure the quality of the water. And many more professionals are directly involved. So safe drinking water is a success story in the United States, apart from what you read in the newspapers. There are all those World Health Organization guidelines. There are now 4 iterations. The 5th set of guidelines is now in development. I'm a member of that committee and have been for many years. And so we are expanding those guidelines to include more components and, of course, also a separate set of guidelines that will apply for recycled water. We have the National Drinking Water Quality Standards. We have those health advisory guidelines for unregulated contaminants. In the United States, we have treatment technology specifications like filtration of surface water, disinfection of groundwater. But when we get to recycled water, because of the origin, the acknowledged low quality of the source water, in addition to all those drinking water standards, it may be appropriate to have some additional specific specifications that are related to the particular origin, what type of a source water is it, and what might it contain that wouldn't normally be in any drinking water source, and what kind of treatment is being applied, and what kind of management needs to be applied to assure successful performance of that treatment. But again, remember, the water that is produced by these high-tech processes is actually better quality than most of the water that is currently considered good quality water, natural good quality water. It's basically rainwater now when it comes out of these recycle plants. So let's talk about some of those specifications that are built into the design of these plants and the operations of those plants. As I said, when we're dealing with microbial indicators, typically the metric is log reductions, starting with some estimated log presence of pathogens in the source water, and then requiring that certain levels of treatment be applied to assure very reliably achieving the sufficient number of log reductions to achieve the appropriate safe water quality goal. Now, in the United States, sort of the rule of thumb for acute contamination risk in drinking water is not more than 1 case of gastrointestinal illness in 10,000 per year. So essentially a nominal upper bound cumulative risk of 1 in 10,000 per year, incrementally above the background. Well, nobody wants to get a gastrointestinal illness, so why 1 in 10,000? Why not 1 in 100,000? Why not 1 in a million? Well, the bottom line is that, as a practical matter, it's very difficult to go beyond 1 in 10,000. And if you compare that to the risk of, for example, foodborne disease, it's significantly lower than the risk of foodborne disease. And in the reality, the actual risk in water supplies in the United States is less than 1 in 10,000 per year. Now, there are 3 major categories of microbial agents that are used: E. coli, viruses, and protozoa. The E. coli are regulated because they're readily measured. Their presence in the source water is there at very high levels. They are not necessarily pathogens, although some of them are, like E. coli 0157, H7. But the general goal range of log reduction is 10 to 12 logs, and it depends which state you're in and which country you're in. But this is a ballpark log reduction, and this provides a significant margin of reduction well beyond the goal of achieving less than 1 E. coli per 100 ml, which is the current regulation. Several logs of safety factor built in here. Viruses, of course, are also present. We don't monitor specifically for viruses because it's too difficult and there are too many of them. What we tend to monitor for are coliphage, which are bacterial viruses that are present in water because there are bacteria in the source water. And so these coliphages prey on those bacteria and produce large numbers of coliphages, which are relatively easy to measure. And we typically also use as an indicator organism MS2 coliphage, and again, a log reduction in the range of 10 to 12, again, to assure risk well below 1 in 10,000 per year. And then the other category of protozoa, in this case, we don't have a generic protozoan. We use actual protozoa measurements because these can be present in source wastewaters. Cryptosporidia giardia, they're less potent than the pathogenic viruses for sure, and so typically a somewhat smaller log reduction is required, 8 to 10 logs generally, but still with a large margin of safety. With chemicals, we deal with chronic exposure risk. We don't really think there's much of a concern about acute exposure risk to chemicals in drinking water. We deal in safe thresholds, safety factors most of the time. In other words, having a database on toxicology, applying a safety factor, arriving at an acceptable exposure for humans that would result in no risk. That's for the traditional contaminants that we deal with. However, there are substances that are genotoxic, carcinogens, and these are substances that could possibly interfere with DNA and cause ultimately some risk of cancer. Now, in this situation, the typical rule of thumb in the United States is to achieve a concentration in drinking water that would be in the range of actually no higher risk than 1 in 10,000 to 1 in a million, or even less, and that's for lifetime exposure. And these are based on very conservative risk calculations on assumptions that even if one of the assumptions is wrong, they're extremely conservative, and if one of the assumptions is wrong, actually the risk model is wrong. So we use very conservative approaches to assure ultimate safety. What about some performance parameters? Well, you have to make good choices on the treatment train based on the contamination that you're trying to remove. And so reuse projects require excellent and reliable wastewater specifications. The wastewater itself, the more treatment that's provided upfront as secondary or even preferably tertiary treatment on the wastewater, the lower the risk, the lower the demand on the subsequent treatments. Now, these wastewater treatment processes are fairly well-known. Biological treatment, of course, solids removal, nutrient removal, reduce the organic carbon, a filtration, which will remove not only particulates, but also many of the protozoa, and then also disinfection, which can kill the bacteria and the viruses, depending on how it's applied. So we start out with a high-quality water, then demands on the subsequent advanced treatment become much less significant. Microfiltration, ultrafiltration, very good for particulates and microbe removal. Reverse osmosis, which is desalination effectively, but it also takes out microbes, inorganics, salinity, and trace organics. There are advanced oxidation processes. The basic oxidation process is ozonation, which can be used for oxidation or disinfection, and it will remove some trace organics. But then there are advanced oxidation processes that use ozone or peroxide in combination with ultraviolet light. These really go way beyond the norm, because at this point in a treatment train, we're probably dealing with a few chemicals at a few parts per trillion. Well, this is really an ultra-conservative approach. There are absorption processes that can be used too, like granular carbon, and they will remove trace organics. And then even UV can be used for microbial control. Now, on the monitoring side, the concept of managing these plants should really apply the Hazard Assessment Critical Control Point approach, the HACCP, or the Water Safety Plan Management concept. And what this means is we want to design the process and operate the process so that at a certain critical control points along the way, if it's meeting the performance expectations there, then we're sure that the final quality of the water will be excellent and appropriate. It means you don't rely on end of treatment management. You manage it at every point along the way to be sure then that you are preventing any adverse outcome by the time the water gets to the end of the treatment frame. So HACCP approaches, Water Safety Plan approaches, the WHO version of HACCP, are very essential to the process. So in conclusion, let's summarize. Any water can be recycled for virtually any use. And so the idea is to choose the source water and choose the treatment process to meet the appropriate end use. And there are many different reuse applications. Some of them involve potable and some of them are not potable. And in fact, the higher volume ones are the non-potable ones. And therefore, cheaper, less expensive treatments can be used for those. Drinking water can be planned indirect potable reuse and planned direct potable reuse. Indirect potable reuse, by the way, has been going on pretty much as long as there have been people on Earth. Because when waste is put into a river upstream and then goes downstream and then is taken out and is treated, that's indirect potable reuse. Direct potable reuse is where you eliminate the river, where you take the wastewater, you treat it, and you can send it directly to the drinking water facilities. Source control is important because the composition of the source controls the needed treatment and the treatment monitoring that is required later. We have very comprehensive drinking water requirements. We do not need new comprehensive recycled water treatment requirements. What we need is some slight augmentation of the current drinking water requirements for the appropriate source and treatment. We have many drinking water standards, and with the same concept, the preventive concept and the multiple barrier concept that is currently operated in drinking water treatment to a lesser degree, however, that works in the determining of appropriate specifications for potable reuse. Real-time monitoring is important because we're dealing with higher risk source water, and therefore as much as possible, real-time monitoring rather than a day or two later is important. And so if one is operating a reverse osmosis system, what you want to do, of course, is be monitoring for factors such as dissolved solids or pressure loss or electrical conductivity. These are real time, and they'll let you know if that process is not working as well as you would like it to do. But you do need some occasional comprehensive monitoring just to be sure that everything is working in the long term as anticipated. And the other thing is that you need a decision logic for managing deviations. You need to know when it might be necessary to divert that treated water. Virtually never, I think, but you need to know what would be the decision rule when it would be necessary to divert that water from the mains. And as Adil said, it's important to engage the public. They will support it if they are convinced first of the need. But history shows that even after they're convinced and after they build the plant, They might not all drink it, but that's an education process, and in time, it will become routine and not a concern. So, thanks very much. This is my contact information if you have any questions later. So I'll turn it over back to Sally.
And Joe, there's a question for you.
Yes.
The question is, under design on operating spec, under which category would algal toxins be put?
Well, algal toxins are interesting because, first of all, they are usually, for example, microcystin LR, which is the most common one, is a very large molecule. It's about 1,000 molecular weight, so it's really easy to take out. Even conventional drinking water filtration plants with a little extra powdered carbon and potassium permanganate will get you down to below detection. If you're dealing with an advanced treatment plant, they will be stopped very early in the process. The main thing, by the way, with algal toxins, first of all, is to separate the algae. Because if you allow the algae into the treatment system, and then you add an oxidant such as chlorine or ozone, what you do is you will lyse the cells where they will then release the toxins. So the first key point is filter out the cells, then put them through the appropriate treatment process, and you will achieve zero in the finished water.